And welcome to my presentation on the topic comparison of different methods to determine volatile matter and carbon content of biochars. My name is Markus. I'm a researcher at the Unit of Technology of Fuels at RWTH Aachen University, and my PhD deals with the pyrolysis of biomasses to get biochar. And there I look more into detail on the processes during the pyrolysis and how different parameters affect the biochar quality and also the quantity. So now I want to present you the results of my current investigation we already did. And I want to start with my motivation, so how I came to this topic, and then I go into the approach and the results of my experiments we achieved so far. And at the end, I want to conclude with the findings we already made. So here you can see the results of a proximate analysis. We investigated 20 biomasses and their biochars, which are pyrolyzed at 500 or 600 degrees. And you can see the fixed carbon content of the biomasses in the green columns and of the biochars in the black columns. And you can see that there is a difference between both. So we have an increase of the fixed carbon content from the biomass to biochar. And the difference is around 5 weight%, sometimes a little bit more, a little bit less. And we now want to have a look on parameters who can influence this and how the fixed carbon content can be determined for biochars. So for those of you who are not familiar with the determination method of volatile matter content, there are 2 standards in Germany, one for the solid fuels and one for the solid biofuels. And they are both done with a muffle furnace, and the only big difference is the grain size. So you put your sample in a crucible with a cover to avoid oxygen content, and put it in a preheated oven at 900 degrees for exactly 7 minutes. And then you can determine the volatile matter content by mass balance. So the fixed carbon content then is a calculated variable. So you take the mass sample minus the ash and volatile matter content in water-free state, and you get your fixed carbon content. So the fixed carbon content can't be determined directly. It can only be calculated. Now in this investigation, we look at different methods. For example, the thermogravimetric analysis to get information about how the mass loss is related to the temperature. And on the other hand, we investigated with a muffle furnace, as it's already done by standard. And there we look at the influence of residence time, temperature, and heating rate. So let's go into the results of the thermogravimetric analysis. There we first have done some experiments with different materials. On the one hand here, the 3 main components of biomasses, so lignin, then xylan as one of the main components of hemicellulose, and last but not least of cellulose. And you can see that the decomposition of xylan starts first between 200 to 300 degrees. And this is followed by the decomposition of cellulose in the temperature range of 300 to 350 degrees. And lignin decomposes over a wider temperature range and is still not completed at 900 degrees. So if we compare this now to 2 biomasses, in this case straw and wood, you can see that the decomposition is something like a mixture of the 3 main components. So you have the main decomposition between 300 to 400 degrees. And above 400 degrees, you have only the lignin, which decomposes. But the the different materials are comparable to each other. If we now have a look on to biochars of the wood and also the straw, you can see that the mass loss is not so high because the biochar is processed by pyrolysis and the volatile matter content is gone for a big amount. So you have a mass loss or you have a residue mass of 80% in this case. And these two biochars are more comparable to fossil fuels. In this case, we investigated hard coal and anthracite. Anthracite is maybe the most degassed fossil fuel we have. So you can see that there is a very low mass loss, and you can especially see that the biochars are in this case more comparable to the fossil fuels than to their original biomasses. And another thing you can see that the mass loss is still not completed at 900 degrees. So if we increase the temperature, there will be a decrease in the mass as well. So now we come to our first results. We adjusted the standard determination method in the muffle furnace for the TGA. So we put our sample for 7 minutes and 900 degrees under nitrogen in the TGA, of course with the heating phase. And there you can see the decomposition, in this case of spruce wood. And as the decomposition is not finished after the 7 minutes, we want to see how the residence time and also the temperature has an influence on this material. And therefore, we investigated the material at 400, 600, 800, and 900 degrees with 3 hours residence time. And there you can see that especially above 600 degrees, the results are quite similar, with the only difference that the mass loss rate at 900 degrees is much higher than the mass loss rate at the lower temperatures. So we think that the mass loss increases with the higher temperature. And the same result, the same determination we also did with other materials, for example, with the anthracite, which you can see here. And as I already mentioned, there's not many volatile matter content in it, so the mass loss is very low. But you can also see that the mass loss rate increases at the highest temperature, so there might be an influence. And what you also can see is that there is no constant mass visible after the 3 hours. That this was the reason why we took longer residence times, and therefore we made the next trial with 60 hours under nitrogen at 900 degrees with 4 samples. And as you can see, after the main decomposition at the beginning, there is a linear mass loss over the residence time. And at the end, you reach constant mass, but this is only the resulting ash of the material, as we also determined by approximate analysis. And also the material looks like the resulting ash. So now we go over to the results of the muffle furnace, as it's the standard determination method. And there we also looked at different influences. On the one hand, the residence time. So we had here, we put 10 samples of spruce wood in the muffle furnace and take 2 of them after 7 minutes out of the furnace, to another after 15, and so on. And you can see that with an increasing residence time, the gas yield is increasing, which is not very surprisingly. And the same is also for other materials, for the biochar and also for the cellulose as one of the main components. and as well as for hard coal. After that, we did another investigation. So we preheated the muffle furnace to 400 degrees and put the sample in it for exactly 7 minutes. And after that, we weigh it and put the same sample after the first treatment temperature in the preheated oven at 600 degrees, exactly also for 7 minutes. We weigh it, and then we did the same at 800 degrees and as well as at 900 degrees to have a stepwise heating of the sample. And in the second trial, we skipped the first treatment temperature of 400 degrees. So there are only the results of 600, 800, and 900 degrees. And in the third trial, we skipped also the 600 degrees. So the sample was heated only at 800 and 900 degrees. And here are the results of this. So first we start with the spruce wood. You can see the gas yield at the different temperatures. And between 400 and 600 degrees, there is the highest gas yield difference. And above 600 degrees, there is not a big difference. And if we now compare this to the second trial where we skipped the 400 degrees, so the sample was heated already to 600 degrees, there is a small difference and a small higher gas yield than in the first trial. And the same trend is visible in the third trial. And now we can compare it also to the standard test method where we put the sample in the 900 degrees preheated oven. It can be seen that the gas yield increases if you do not stepwise heat the sample, but if you heat it up very fast. The experiment was also done with other materials, in this case with the biochar, cellulose, and anthracite. And with cellulose, you can see the same trend as for the spruce wood, as it is one of the main components. But what's interesting is that the biochar and also the anthracite has a different result. There is no influence visible of the stepwise heating. So the resulted gas yield at 900 degrees is always the same. It doesn't matter if you heat it slow or fast. So if you remember the slide of the beginning of my presentation, there I showed you the difference of biomass and biochar fixed carbon content, around 5%. And now we did the same investigation of biomass and biochar when we put the sample in the cold oven and heated up from ambient temperature to 900 degrees, and did the same for biomass and biochar. And there you can see that the difference between both samples is not that big, in most times lower than 5 weight%. So this confirms that the influence of heating rate is existent in this case. Last, we want to investigate the influence of the heating rate on the structure. So we took wood sample and pyrolyzed it to 900 degrees. On the one hand, very slow, so from ambient temperature to 900 degrees. And as you can see by comparing the two pictures, the structure of the wood is largely intact. So yeah, it seems like that there's not a big change in the surface structure. And now we can compare it to the fast heating. So we put the sample in the preheated oven, and there is a bigger change in the surface structure. So there's something like the structure is a little bit cracked, and yeah, it doesn't look like the biomass before. So to conclude the results we've done so far, there's a different residue amount of biomass and biochar. The residue amount in this case is on the one hand the ash content, and on the other hand the non-volatile components or the lower volatile components. And we investigated the influence of different parameters, in this case temperature, residence time, and heating rate. And as you can see, with an increasing temperature and residence time, you have in all cases a lower residue amount for biomasses, biochar, and also fossil fuels. And now the interesting thing is that the heating rate has a different influence on the three materials. So with the biomasses, there is also a lower residue amount, but for the biochars and fossil fuels, there is no visible influence of the heating rate. So we think that the heating rate has an influence on the structure, so that there is a reconstruction of the surface of the material, which can influence the method to determine volatile matter, and in this case also the fixed carbon content. Now I want to thank you for your attention, and I hope you enjoyed my presentation.
Yes, we enjoyed it very much. Thank you so much. Very interesting presentation again, and I'm looking forward to questions. That's the obvious question. Wouldn't it just compensate the changed structure to have a longer heating phase or longer duration of the heating for the stepwise heating, just to get out the rest of the volatiles?
You mean if you have the longest residence time of maybe some days or something like that,
yeah.
And that the structure remains in this case like the biomass, or what do you mean?
Yeah, just to get out the last volatiles.
Yeah, I think this also, when you remember the slide of the TGA experiment where we did it for 60 hours, it was a very small amount there, maybe 100 gram or something like that. And at the end there was only ash. So I think if you have a long residence time, there the whole carbon content is gone in this case, and also the whole volatile matter in it.
Okay, very good. So there is a question from Maximilian Walzer.
Yes, thank you for the presentation. You analyzed all those fuels, but I wonder, does it have any practical consequences for ovens or for boilers, or where do you see some practical consequences of your results?
Yeah, I think it's on the first hand a consequence for the analysis of these materials. So now you analyze biochars, or you do not know which standard you should use for biochar analysis. You have the one for the biofuels and also that one for the fossil fuels. And we want to see which of the standards is the best for it, because the biochar has characteristics of both of biochar, of biomass, and also of the fossil fuels. And at the end, maybe also the processes of pyrolysis and biochar production can be influenced by it, so that you can lower the temperature, so you have more time to leave the sample in the oven to get a higher carbon content, but to also have material at the end you can use for your application.
Thank you.
Okay, thank you. So I see two additional questions. The next one from Hossein Bedaki. There's still no audio signal connected to unmute you.
Jürgen, maybe I fill the time because this is the answer to the question before directly. So where we see the sense of this work is, well, we are questioning the expression volatiles, because this is not a fixed number for a fuel. It's also a function, or it's a function of temperature and residence time. So fixed carbon is just the right expression if you give the time of heating. And so if you say you make an approach after the DIN XY, I don't know the number at the moment, but where you heat the 7 minutes to 900 degrees, then you can do this. But you can't compare it with a thermogravimetric analysis, as you saw, because you have different results. And in literature at the moment, this is done because everybody says this is a fixed carbon. They do something for some time in nitrogen, and at the end they have a solid, and they say this is the fixed carbon, and all the volatiles are gone. But we think volatiles can also come from the fixed carbon if the time and the temperature is high and long enough. This is, I think, the message, the main message, and we want to look further. How can we influence this, and what is, of course, also the impact on the practice?
Okay, thank you for the comment. I guess we still have a technical problem with Hossein Bedagi's audio because I cannot unmute him. Can you perhaps address your question in the chat? Or do we have a solution from the... Oh, now it works. Okay, now just go ahead, please. Sorry, different persons on the web. Yeah, please. Now it should work, Mr. Bedagi. Or
you can write it in the chat and I will answer it.
So now, can we hear you now? Still not. Maybe you should just use the chat, please. Maybe I can fill the time between.
He will send a message via chat. He sent me a message.
Okay. Perhaps to fill the gap, short question from my side. What about inorganic? So you also have some potassium components, and so also being released at temperatures above 500, 600 degrees. Do you really, or is it really only volatiles that you measure in your experiments, or what is the influence of salts and inorganics that go to the gaseous phase during the heat up?
Yeah, I think that there's an influence, especially because you heat up to 900 degrees, and there will be also, you have the difference method also for the ash content. You have the biomasses is the ash content determined at 550 degrees, and for fossil fuels at 815 degrees, because of the ash contents, which have an influence there. And yes, I think that they have also an influence by determining the volatile matter, but this was not what we've concentrated on so far.
Okay, does anybody see the question from Mr. Baidagi in the chat?
Yes. In TGA, we can only use mg of the samples. However, the nature of the biomaterials is non-homogeneous. So to get the representative data, it is better to repeat the experiments in STA or TGA.
Yeah, we have done the experiments in different furnaces, not only in TGA, but we investigated also in bigger furnaces. So and on the other hand, we have also done it with some of the biomass components of the cellulose, which I think should be more homogeneous than wood, for example. And yeah, there's a lot of work to do, but I will consider that we look on the heterogeneous of biomass.
Okay, thank you so much. So I hope that answers your question. And so
otherwise, you can write in the chat.
Yes, of course. So that means we also have to look for the time. And thank you again, Markus Lang, for that very nice presentation.